Hi everyone. Today we will develop a function for OLS regressions and try to replicate the output of built-in OLS modules in Python. It is always a good idea to know what goes on inside the code behind the final output. I'll do this video in two parts because it gets a bit long if I do all of them in one video. So let's get started. So what I have here is a sample data that I'm going to use to show you guys how to do this thing. So my sample data is US macro indicators. It consists data on consumption, GDP, and interest rate. So I have defined my X matrix, which has a column of ones, a column of GDP, and a column of interest rate. And so the first thing that we're going to do is we're going to use the Statsmodel package in Python to get some OLS results. So this is just a random regression that I have done to compare with my function that I'm going to write down. So Statsmodel gives us these OLS regression output when I regress consumption on these three covariates. And we can see that these are the estimates and these are different parameters related to the fit of the model. So in part 1, we are going to replicate all these estimates, and in part 2, we are going to replicate these parameters. So let's get started. So the first thing that I'm going to use is I'm going to import NumPy, because this is what we are going to use to write our function. And then I'm also going to use the t distribution from SciPy. Right. So let's get started. Let's name our function OLS. It will take input of y and x. So it's always a good practice to write some description about our function. Maybe I want it to look like this. So it takes two arrays as an input and gives a model as an output. And I can also write that as input, y is the dependent variable and x is the independent variables. And the output of the function is going to be model summary. Right. So the first thing that we are going to do is estimate beta of all the covariates. So I'm going to use linear algebra, which is the x prime x inverse 1 x prime y formula. numpy.linearalgebra.solve. I'm going to use solve instead of the inverse because solve is computationally less cumbersome in Python than doing an inverse of a matrix, x prime x and x prime y. So it's going to solve the equation x prime x equals to x prime y, and the solution is going to be our beta estimates. I'm also going to reshape this just to make sure that it is arranged as a k by 1 matrix. Right, so now we have the beta estimates. Let's see if this works out. So let's do OLS. Dependent variable is consumption and independent variable is x. So we have 36, 0.67 and minus 25. Let's see, 36, 0.67 and minus 25, right. So our function is going right. So let's continue. So now this is our regression coefficients, and now we are going to get the predicted values and residuals because we need this. So y hat is the predicted values, which is just the matrix multiplication of x and the beta matrix, and then residuals is just the difference between y and y hat. Now let's specify the number of observations, covariates, and degrees of freedom. So n is the number of observations, so it should be equal to the length of our dependent variable in this case. K is the number of covariates, so it should be equal to length of beta, and degrees of freedom is n minus k. Alright, so now let's get the variance of the regression, which we are going to get. So the formula for sigma square is SSE divided by n minus k. So the first thing we need is SSE. So sum of squared of residuals. So I'm going to use the residuals and reshape it into a 1 by n matrix, and matrix multiply it with the same residuals reshaped as n by 1 matrix. So a 1 by 1 n matrix multiplied by a n by 1 matrix will give us a 1 by 1 scalar. So we will get the sum of squared errors. Now let's get the sigma, which is the standard deviation of the regression, which is square root of SSE divided by its degrees of freedom. And we can similarly get sigma square, which is just the square of sigma. So this is the variance of the regression. Now we know that the standard error of the covariates are just sigma squared into x prime x inverse 1. So I'm going to use that formula. Standard errors. So the first thing is, let's get the variance covariance matrix of our beta, and this is going to be sigma squared into inverse of x prime x. So it's x prime x inverse 1 into sigma square. That is going to give us the variance covariance matrix, and the diagonals of this matrix have all the variances. So I'm just going to extract the diagonals from here. And then I'm going to reshape this as a k by 1 matrix. So standard errors are just the square roots of the variances. Alright, now let's get the t statistic. So for the t's, so the t stat. So in this case, t stat is just going to be beta divided by its standard error. And let's get the p-value. So we can also write it in a way that we can input the alpha, or the level of significance within our function. So let's go ahead and do that. So let's include alpha as an input, and I'm going to make it an optional argument. So if alpha equals to none, then alpha is equals to 0.95. So if no input is given, it's just going to set the default to 95%, and if some input is given, it's going to take that as an input. So we need the t stat, we need the t score from the t distribution. So t.ppf, which gives us the PDF of the t distribution, and the first argument is going to be alpha plus 1 divided by 2, and then the second argument is just going to be the degrees of freedom. And now p-value is equals to, so we're doing a two-tailed test by default, so p-value will be two-tailed based on the two-tailed test here. So I'm going to multiply 2 with it, and then 1 minus the CDF of the t distribution. So t dot CDF, absolute value of beta, then the degrees of freedom, and the scale parameter, which is the standard deviation, is just going to be the standard error of that covariate. So this should give us the p-values. So let's finish this video at this point. So I'm just going to write down the print command to see if we can replicate up to the p-values along with the Statsmodel package. So let's print out the results. So for I in range, okay, so I'm using a loop to print out for each of the covariates. Print, and then format it, coefficient and the space, coefficient, and so the first line is going to be coefficient 0. So this indicates that the following codes will be the statistics of that coefficient. And then let's print the other things. I'm going to use 4 ones here, format. And so the first thing is beta. Let's index this with I. Okay, so this is going to print out the beta estimate. And let's print, format it as, so now we're going to print out the standard error. I'm going to copy this. Now let's print out the t statistic. And now let's print out the p-value. And let's give a separator. So let's see if this function works. I'm going to run it here on top of it. Results is equals to OLS. Dependent variable is consumption, independent variable is X. So something. Okay, so we have a typo in SSE. Let's fix it. Let's run it again. Nice. So you can see that we have coefficient 0. This is the first one, 36.64. And yes, it is 36.64. Its standard error is 16 and t-stat is 2.21. Let's see. Yes, standard error is 16 and t-stat is 2.21. And it has a p-value of 0.27. And we have a p-value of 0.28. Yep, this is 278. So we can see that our function works pretty well up to p-value. In the next part, we are going to write the code for rest of the statistics. Thank you.